for you to add radical expression, the one thing, well, or the two things that you need to have is you need to have the same root. If you have a square root on one item, you have to have a square root on the other item. And you need to have the same radicand, meaning the number inside your root. So number one and number two have to be the same in order for you to add. If one of them are not the same, you either have to try to find some way to make it the same in terms of the radicand. The root, you cannot make it the same. If one of them square root, the other one is a cube root, there's nothing you can do, okay? There is something you can do, but we will not go there. We will not take that route, okay? So for now, just know that if we have different root, there's nothing you can do, okay? But if the radicand, if the number in the root are not the same, you have to ask yourself, is there a perfect square hidden, and somehow make the radicand to be the same? Once you have it, all you need to do is add the coefficient, which is the number in front of the root. You add them up and you kept the square root or the cube root, and you kept the radicand, right? So in terms of A, we did this last time. We have 4 square root of 5x plus 17 square root of 5x. All we do is we take the 4 plus 17 to know, in short, or to know that we only have 21 square root of 5x. The square root of 5x will never change. You will never ever add the item inside the radical, okay? So we mentioned this item here. Like I mentioned, if we have the same cube root of 7, cube root of 17y, cube root of 17y, cube root of 17y. And again, in a sense, all we do is we take the cube root of 17y and then we add or subtract what the coefficient that we have. So we know that 23, take away 5 to give you 18, and 18 plus 2 to give you 20. So in total, you have 20 cube root of 17y. So we stumble to this problem, and this is where I mentioned to you guys that this is where the problem come in, is our root, we have a same root. We have a square root of 3, a square root of 27, and square root of 12. And in order for us to add the radicand, meaning again, the 3, the 27, and the 12, those items need to be the same, right? If it's not the same like this case, if it's not the same like in this case, again, this item here, we know we have a square root, so that's good to go, right? We have a square root 3, square root 27, square root 12. Now we say, well, the radicand are not the same. So what do we do? Before we can say this is our answer, we have to ask ourselves, is there a perfect square inside 27? Is there a perfect square inside 12? And we did this in terms that we say, well, 27, instead of say 27, we can say 9 times 3. And instead of say 12, we can say 4 times 3. And why do we use 4? And why do we use 9? Because 4 is a perfect square and 9 is a perfect square. Because 3 times 3 is 9. So therefore, you can bring out a 3. And whatever you bring to the outside, all we do is we multiply to the number on the outside of that radical. So again, why is we using 4? Because 2 times 2 is 4. I bring the 2 on the outside, and when I bring it outside, I multiply to the number. Again, there's nothing you bring here. You can bring it 1, but 1 times 7 still 7 square root of 3. So once you bring it out, once you take out the perfect square, this is what we have, which is 7 square root of 3 plus 39 square root of 3 minus 10 square root of 3. And this is what we want to see, right? This is what we want to see, is a square root of 3, a square root of 3, and a square root of 3. So if the square root of 3 is all the same, now we can add, right? We can take 7 plus 39 to give you 46. 46 take away 10 to give you in the total 30, in the total of 36 square root of square root of 3, right? So we went over this the last time, and we go over the other problem, but let's take a look at the next set of problem in this PowerPoint that we did go over last time, and then hopefully the second time you see it, hopefully it's a little bit better, right? So I mentioned this earlier in terms of D. I mentioned that this thing here, if you look at this thing, you see that square root 15 and cube root 15. I agree with you guys that you say, well, the 15 and the 15 is correct. The 15 and 15 is the same, yes. But we still cannot do anything in terms of this thing is a square root if there is no number is a square root, and this thing is a cube root. So the root are not the same, and if the roots are not the same, doesn't matter what the number on the inside, we still cannot combine them, okay? Like I mentioned over here, we have a square root of 5 and square root of 3. We cannot combine them because the number are not the same. Okay, so you need to have the same number and the same root. If the number are not the same, we cannot combine like this item here. This will be your answer. Please do not give me a square root of 8. We do not add the item inside your radical. Okay, so this right here, this is your answer, square root 3 plus square root 5. We're done. If this were to be a problem that they give you here, this would be your answer, a square root of 15 minus a cube root of 15. That's it. Those are your answer. There's nothing you can combine. Okay, so let's take a look at this item here. You wish we have a lot of item like D, right? But again, you won't see a lot of item like D. You see a lot of item like E, right? So let's take a look at E here, and before we can jump to the conclusion that this is my answer, there's nothing we can combine, right? Before we can say, oh, E just look exactly like D, right? Before we can jump into that conclusion, the first thing you need to ask yourself is there any perfect square lingering around inside my square root of 24? Right? So one thing is 24, hopefully you guys see that this is what we have. Do you agree that 24 is equal to 4 times 6, right? And why do I use 4 times 6? Because 4 is a perfect square. Ladies and gentlemen, 4 is a perfect square. So everybody see that 4 is a perfect square, meaning this item here, I can take this item and I say square root, right? Square root of 4 times 6, which is the same as a square root, well, not the same, which is the same as 2 square root of 6. Meaning the 6 is not a perfect square, so the 6 stay on the inside, right? The 6 stay on the inside because the 6 is not a perfect square. What can go out of the square root? The only thing can go out of square root is a perfect square. In this case, is 4. Why do I emphasize this? Why do I mention this? Because if inside a square root of 6, if inside a square root of 6, the remainder is 6, this is what you want to ask yourself is 150, can 150 divided by 6? Okay, that's what the reason is if one number have a square root of 6 on the left over, then mostly, and again, hopefully you guys see it right here, 54 is the same as 9, 6 times 9, right? 9 times 6 or 6 times 9, right? That's 54. And why do I attack using the 6? Because the 24 have a remainder of 6. The 54 should have a remainder of 6, which is 9 is a perfect square. So we good to go. So now 150, you ask yourself, well, does 150, can 150 divided by 6? And in this case, you can see that 150 is the same as 25 times 6. Hopefully, right? 25 times 6. And why do I attack that number? Because like I mentioned to you guys last time, this is what you want, right? This is what you want, is you want to find a perfect square inside your number and attack the small number. If you have a small number, attack the small number, ask yourself, what is the remainder if you take out the perfect square? And again, 4, the perfect square is 2. 25, the perfect square is 5. And 9, the perfect square is 3. So this is what I took out, right? I took out the perfect square is 4. The perfect square is 4, so I took out 2, right? The perfect square is 4, I took out 2. The perfect square is 25, I took out 5. The perfect square is 9 on the inside, so I took out 3. There's nothing in front of this square root, so there is basically just 2 because it's 2 times 1, right? This, we still have a 2, so 5 times 2. This, I have a 4, so 3 times 4. So basically, I took out the square root. I took out a perfect square, and this is the perfect square when I took it out, which is the 2, the 5, and the 3. Now, what do? I just multiply to my constant on the outside. So I have 2 minus 10 plus 12. And again, this is our goal, and this is probably the challenging part that a lot of you guys have, is how can you take this number here? How can you take this number, 54, 150, and 24? How can you take those number and extract out the perfect square, right? Extract our perfect square to give you a square of 6, a square of 6, a square of 6. Because once you see that we have a square of 6, a square of 6, square of 6, all we need to do is add or subtract the coefficient. 2 take away 10, that will give me 8, right? 2 take away 10, that will give me 8. Sorry, negative 8. Negative 8 plus 12, that will give me 4. And again, a square root of 6 is just remainder as a square root of 6. Because I have a square root of 6, I have 2 square root of 6. Take away 10 square root of 6, I have 8 square root of 6. And 8 square root of 6 added to 12 square root of 6, I have a total of 4 square root of 6, right? The square root of 6 is just think in terms of like a figure of speech, right? Think in terms of $6 or 6 cow or whatever, right? So it's just a figure of speech. The square root of 6 will never get added, right? We just add the coefficient. So question here, ladies and gentlemen, question with E, in terms of how can you extract the perfect square out and then add or subtract the coefficient. Now, I believe I have one more. Let's try one more, right? Let's try similarly with this item here. You can see that we have 45, 20, and 500. And again, before we can make a determination, say, this is my answer, Mr. Tran, there's nothing I can do. Before we can do that, you have to ask yourself, is there a perfect square, right? Is there a 4? Is there a 9? Is there a 16? Is there a 25? Is there a 36? Is there a perfect square inside your 49, 45, 20, 500? And attack the 20 first, right? Attack the 20. Attack the 20, which looking at this thing here, if you look at the 20, do you agree that 20 is equal to 4 times 5? And why do I say 4 times 5? Because 4 is a perfect square, right? So 4 is a perfect square. The leftover is 5. So mostly you guys will say, well, if 5 is the leftover, can 45 divide by 5? And in this case, 45 divided by 5 will give me 9, or the same as 45 is equal to 9 times phi, right? And again, if you see that the phi is left over, you just ask yourself, can 500 divide by phi and 500 divide by phi to give you 100? Or in the same token, 500 is the same as 100 times phi. And as you can see, all of them have a leftover phi. And that's one thing, is whatever they give you, the leftover will be the same, right? Because all of them will have a square root of phi. And we know 100 is a perfect square, 10 times 10. We know 9 is a perfect square, 3 times 3. We know 4 is a perfect square, 2 times 2. So if we have something like this, right? If we have something like this, you want to attack the smaller number and ask yourself, what is the leftover, right? So again, the 9 in the first item, the 9, I know that I can bring out a 3. So 3 times 4, that will give me 12. The 4, I can bring out a 2, 2 times 3. And the 100, I can bring out a 10, 10 times 7. And as you can see, or many of you probably saw it, the square root of phi, square root of phi, square root of phi, all of 3 of this thing here is the same. So once all 3 of them is the same, all we need to do is add or subtract the coefficient. So this is what we have. 3 times 4 is 12 square root phi. 2 times 6 is, 2 times 3 is 6 square root phi. And 10 times 7 is 70 square root phi. And what do we do? All we need to do is take 12 plus 6 minus 70. We take the coefficient and add them up or subtract them. 12 plus 6 is 18. 18 take away 70 will give you 52. So we have a negative 52 square root of phi. So ladies and gentlemen, question with this particular problem, how did I take this problem up here? 4 square root of 45 plus 3 square root of 20 minus 7 square root of 500 and simplify them to be negative 52 square root of phi. Any question with the meter of this process? Any question here? Well, if you don't have question with question.
Oh no, I see what I did wrong. Never mind. I'm sorry.
No problem. All right. If you don't have question with adding or subtraction, let's pause with this item for now. Let's go to the next section, which is 10.5, and see what we need to do with multiplication. And later on, how do we do with division? So multiplication is a little bit easier. And a small rule of multiplication that is different from the addition is, remember, for addition, all you need, well, addition is restricted, right? You need to have a same root and a same radical, meaning the number inside the root, in order for you add the coefficient. To multiply is a little bit less restricted. The only thing you need is you need to have the same root. You need to have if you have a square root, you need to multiply to another square root. If you have a cube root, you need to multiply to another cube root. Once you see that you have the same root, then all you need to do is take the whole number, which is the constant, the coefficient, multiply with the coefficient, and take the radicand and multiply with the radicand. So basically, this is all we do is we take 2 times 6, that's your coefficient, that's your the whole number, right? 2 times 6, and then inside the square root, the radicand, which is 7 and 11, 7 times 11, and in this case, this is what we have is 12 times 12 square root of 77. And the 77 does not contain a perfect square, so you don't need to, this is your answer. If there is something that contains a perfect square, then you need to reduce them or simplify them by extract out the perfect square. Okay, so again, in short, this is all we have, right? In short, this is all we have. If we have a 3 square root of 2 times 4 square root of 3 minus 7 square root of 13. Reminder inside here, you cannot subtract this item, right? 4 square root of 3 minus 7 square root of 13. You cannot subtract this and give me 3 square root of 10, right? We cannot do it because remember, in order for you to add or subtract, the radicand, the number have to be the same. The 3 and the 13, they are not the same. You cannot do it. The 13 is prime, the 3 is prime. There's nothing you can do. So if you were to have this problem, and if there is a parenthesis, and just like before, right? Just like before, all you need to do is, in order for you to multiply, we need to distributive this item in, right? We need to distributive this item into both of this item. And basically, or technically, this is what you do is you take the 3 square root of 2 times 4 square root of 3 minus 3 square root of 2 times 7 square root of 3. And again, as you can see, we convert this problem to 2 of the example A problem, right? This is just the same as this, just different number, right? So we just imagine that we have 2 example 8 once we distributive them in. So once you distributive them in, the first item, you have 3 times 4 in the outside, right? 3 times 4 on the outside and 2 times 3 on the inside. And on the second item, you have 3 times 7 and 2 times 13. 3 times 4 to give me 12 square root of 6, and 3 times 7 to give me 21 square root of 26. And again, 6 and 26, they do not contain any perfect square. There's nothing you can do in terms of subtract them, and this is your answer. And again, sometimes your answer look a little bit massive, but this is the answer nevertheless. Okay, so again, looking at this thing here, as you can see, to multiply radical, all you do is the constant times the constant, the radicand, the number under the radical, times the number under the radical. Okay, so let's take a look at C. And again, similarly with this item, with a small exception of something, but looking at this thing here, as you can see, we have this item we need to distributive in, and we have this item we need to distributive in, right? To get rid of the parenthesis, just like before, just like every time we have something outside of the parenthesis, we need to multiply, distributive them in, and this is what we do. Or technically, this is what we do is we take 6 square root of 3 times 2 square root of 6. 6 square root of 3 times 11 square root of 15. And once we have this thing here, we know that in the first item, we have 2 times 6. 2 times 6 to give us 12. So, excuse me. 2 times 6 to give us 12 on the outside. 3 times 6 to give me 18 on the inside. 6 times 11 to give me 66, and 3 times 15 to give me 45. So unlike the previous problem, and this is probably the hardest thing that for most of you is, if you say that this is the answer, sometimes Connect Math or MyMathLab for you guys will tell you it's wrong because it's not in the simplest form. It basically tell you that inside here, inside the 18, there is a hidden perfect square, right? Inside the 18, before we can let go and say this is our answer, remember 18, you have to ask yourself, is there a perfect square in 18, right? And same thing goes with 45. Is there a perfect square in 45? And hopefully you guys see that 18 is the same as 9 times 2. Why am I using 9 times 2? Because 9 is a perfect square. And 45 is 9 times 5. Why am I using 9? Because 9 is a perfect square. So again, before we can move on, we have to ask ourselves, in this item, is there a perfect square? And with this item here, we do have a perfect square. And if we have a perfect square, we bring out a perfect square. In this case, we bring out a 3. Again, inside the radical is 9, but when you extract them out, you extract out only 3. And so 3 times 12 to give me 36, 3 times 66 to give me 198. And now this is our answer, ladies and gentlemen. There is nothing we can add because square root of 2 and square root of 2 and square root of 5, they are uncommon radicand, right? The number are different. So this is all we have. We have 36 square root of 2 added to 198 square root of 5. Question with A, B, or C here, ladies and gentlemen. Question with multiply and so forth. Again, you know, one thing I know, one thing I think I know, if you have problem, the only problem that you have with this radical is you know, how do you know, the hardest thing I think that many of you guys encounter is how to extract out a perfect square, right? If you look at the number, how do you do it? You know, unless you're good with your timetable, if you're good with your timetable, then you can see it right through. If not, you know, you have to ask yourself by using your calculator, right? Take that number, divide it by 4, divide by 9, divide by 16, divide by 25. Why do we divide by those numbers? Because those are your perfect square number. If you can divide by those number, then you have a perfect square, right? So again, just practice a little bit. You should be able to recognize it. You know, so let's take a look at D, right? Let's take a look at D. How would we go about to simplify this item here? So if you look at this thing here, this thing is just the same as chapter 5 when we multiply a binomial time a binomial. Meaning, if you look at this thing here, this is what we're doing is we FOIL this thing out. Or in a sense, as you can see, all we do is we take the first item, multiply to the first item, take the outside item, multiply to the outside item, right? Take the inside item, multiply to inside item, and take the last item, multiply to the last item. So basically, all we're doing here is we distributed this item in, ladies and gentlemen. So if you take this, you know, red item 2 square root of 3 times 3 square root of 5, same idea go 2 square root of 3 times 6 square root of 2. And then I put the blue arrow, which is 5 square root of 7 times 3 square root of 5, and 5 square root of 7 times 2 square root of 2. And the reason why we have a negative here is because of the 6. The reason why we have a negative here because of a negative 6 square root of 2 here. So everybody see that technically all we do is we take the first term, multiply to the second parenthesis. We take the second term and multiply to the second parenthesis. And again, basically now, hopefully now you guys see that we basically have 4 individual problems, right? We have a 2 square root of 3 times 3 square root of 5, which is 2 times 3 on the outside will give me 6. 3 times 5 will give me 6 square root of 15. And then we have 2 square root of 3 times 6 square root of 2, which is 2 times 6 is 12, and 3 times 2 is 6. And then we have 5 times 3 and 7 times 5, and 5 times 6, 7 times 2. So again, basically we have 4 individual problems. And as I mentioned earlier, this is what we have, right? As I mentioned earlier, this is what we have is 2 times 3 is 6. 3 times 5 is square root of 15 on the inside. 2 times 6 is 12. 3 times 2 is 6. Square root of 6 on the inside. Again, 5 times 3 is 15. 5 times 7 is 35 on the inside. And 5 times 6 is 30. And 2 times 7 is 14 on the inside. And again, 15, 6, 35, and 14. First of all, they do not look the same. They are not the same. There's nothing we can add or subtract here. And none of the number have a perfect square in there. So this will be, I know it's look massive. I know you say this answer look very ugly, but it's still the answer we're looking for, right? We are not looking for the, sometimes it's look like this, sometimes you can combine them. But again, this thing here, don't force it, right? I give you this problem just to tell you that if they do not look the same, and if there's nothing you can extract out, if there's no perfect square, then don't force it and add them or subtract them. For addition and subtraction is not flexible, right? In order for you to add, they must have a same square root, and they need to have the same number inside your square root. So looking at this item here, question with D here, ladies and gentlemen. So let's take a look at what happened. And again, hopefully bring back memory. But what happened if we have something like this? and the only thing that you look at this thing and you say, wow, this thing looked like chapter 5. It does look like chapter 5. The only thing that is different from chapter 5 is chapter 5, you have a 3x, or you have an x, you have something. This one, you have a radical. And it's just the same as a radical. Square root of 11 and square root of 5, just imagine it's like an x and a y, right? A square root of 11, square root of 5, they are not the same. So you cannot add or subtract them. Okay, so if you look at this thing here, what do we do? Well, do you agree that a square root of 11 minus 2 square root of 5 square is the same as square root of 11 minus 2 square root of 5 times square root of 11 minus 2 square root of 5? Again, what does the square tell me to do? The square tell me whatever in my parenthesis, I write it twice. 1 time here, 2 times here, which that's the rule of the square, right? The square is whatever your base is, you write that many times, right? So once you have this, and as you can see, the connection of this E problem is we take the first item, we distributive them in. We take the second item, we distributive them in. Which the rule is the same. We haven't done anything wrong, right? The square tell me to write it twice. Once I write it twice, I distributive them. Unless, for those of you who remember your special rule, right? Take the first term square, take the last term square, put the 2 terms together and double them up. It's the same idea. It's just that we do it instead of x, y, or z, we deal with the square root of 11 and the square root of 5. But looking at this item here, let's do it, break it down. Do you agree that the square root of 11 times square root of 11, right? Square root of 11 times negative 2 square root of 5, which is square root of 11 times 2 square root of 5, the negative on the outside. Negative 2 square root of 5 times negative 2 square root of 5, that's what I have. Negative 2 square root of 5 times square root of 11, I should say. And then negative, and I'm about to say right here, this is a negative times a negative, and a negative times a negative, that is why right here I have a positive here. So whoever say why this is not a negative, because a negative times a negative will give me a positive. Okay, so this is what we run into, or this is what we have, is when we distributive, and again, the red ink refer to the red arrow. This is red ink, red arrow. Blue ink refer to the blue arrow. And do you agree that, again, let's do it step by step. 11 times 11 on the inside, we still have 11 times 11 will give me square root of 121. 2 times 1 will give me 2, 5 times 11 to give me 55. 2 times 1 is 2, square root of 5 times square root of 11 will give me square root of 55. And 2 times 2 is 4, 5 times 5 is 25. Everybody see that I just take the outside times the outside, the inside the square root times the inside the square root. And now looking at this item here, hopefully you guys recognize that this is your like term. And they do not cancel out, ladies and gentlemen. We have a -2 and a -2. They are same sign. You need to add them up and keep the sign, which is -4 square root of 55. Now, what is the unique thing? What is the unique thing about 121? Hopefully you guys see that the unique thing about 121 and the unique thing about 25 is they are a correct perfect square, which because of 121, I can take out 11 because it's a perfect square. And because of the 25, I can take out a 5 because it's a perfect square. There's nothing left over. It's a perfect square. Everything go out, right? Which in this case, 4 times 5, and this up here is 11. And like I mentioned, the reason I have a -4 square root of 55 is I have 2 here, 2 here. I add them up. I have 4 total square root of 55. And again, they are negative. Now, do you agree that this is what we have is 11 minus 4 square root of 55 plus 20? And 11 plus 20, those are my like term. 11 plus 20 will give me 31 minus 4 square root of 4 square root of 55. And again, 55, they don't contain a perfect square. So this is your answer. And if you have this answer, ladies and gentlemen, if you have this answer, they want you to write a whole number first. And the reason is sometimes if you put -4 square root of 55 plus 31, sometimes you extend this root to make it longer. So again, you don't, if you have a number and you have some square root, you write a number first, okay? Let's try another one here. Let's take a look at this item. And see this item and the E, see what's the difference between the two. So if you look at this item here, same idea go. Do you agree that a square root 3 minus square root of 7, there's nothing you can do? Square root 3 plus square root of 7, there's nothing you can do. What you can do is you can multiply, and if you multiply a square root of 3 times square root of 3 will give me 3 times 3 on the inside. Square root 3 times square root of 7 will give me 3 times 7 on the inside. And again, 7 square minus 7 square root of 7 times 3 to give me square root of 7 times 3, and square root of 7 times square root of 7 to give me 7 times 7 on the inside. And hopefully you guys see that this is what we have. Many of you probably skipped this step right here. You can see that 3 times 3 on the inside is the same as 3 on the outside. 7 times 7 on the inside is the same as 7 on the outside, right? Because 49 is a perfect square. To get rid of the radical, you need a perfect square, or you need a pair of 2 of the same number. Now, very unique. This is the unique thing about this problem is we have a positive square root of 21 and a negative square root of 21. Everybody see that if you have one square root of 21, take away 1 square root of 21, they cancel out, right? They cancel each other out. So this thing here, they disappear. And that's why a square root of 9 is 3, square root of 49 is 7. That's why I only have 3 minus 7. And what is 3 minus 7? This will give me 4, or in terms of this -4. Okay, so again, this is the answer you're looking for, right? This is the cleanest answer we ever have, right? All of this thing here is simplified just to be this number -4. So looking at this thing here, all we did was we tried to FOIL them out, right? We tried to multiply them, FOIL them out. So question with this item here, ladies and gentlemen. Question with this FOIL multiplication. Let's see. I have one more. Similarly, right? Square root of 11 times 5. I mean not times. Square root of 11 plus 5 times square root of 11 minus 5. So if you do this item, as you can see, we have first time first, outside time outside, inside time inside, and last time last, which square root of 11 times square root of 11, which is 11 on outside. If you see this, 11 times 11 under the radical, it's just basically 11 on the outside. Negative 5 times square root of 11 to give me negative 5 square root of 11. 5 times square root of 11 to give me positive 5 times square root of 11. And 5 times a negative 5 to give me negative 25. And hopefully you recognize, and this, ladies and gentlemen, we call a conjugate of each other, like I mentioned in chapter 5, when you have everything the same, square root of 11, square root of 11, 5 and 5, when you have everything the same, the only thing different is the sign, right? Everything is the same. The only thing different is one of them is positive, the other one is negative. This is the conjugate of each other. And the conjugate, what is the unique thing about the conjugate? The conjugate is the middle term, they will disappear, right? They will cancel each other out. One positive, one negative, they cancel out. And this will give me 11 take away 25 and 11 take away 25 to give me a negative 14. And distinguish, right? Distinguish the difference between, you say, wait a minute, Tran, again, what's the difference between this versus this? Well, in E, one of, right, in G or in G or in F, one of them is positive, the other one is negative. In G, one of them is positive, the other one is negative. But in E, both of them are negative, right? In E, they are not one positive, one negative. They have both of them are negative, which that's why you cannot cancel them out. Okay, so again, F and G is a conjugate of each other, and if it's a conjugate of each other, the middle term will always cancel itself out. Okay, so looking at this thing here again, question with multiplication radical. Well, I guess we can. This is a good. My animation came in a little bit late. I think this is a good place to start for today. We have 11.5, which is division. Not really division, is rationalize. The denominator, and rationalize the denominator is basically the goal is the denominator cannot contain a radical. Okay, so we will pick up on this tomorrow. We will pick up on this the next time I see you, which is tomorrow. So